Cool. Sweet. So I'm thinking to do the other bit that I've offered up yesterday, which would be to, put it that way, shrink the sine wave inside a fixed period duration. So the first thing, I believe I've talked about it last year, but it's worth repeating. A few bits about how sine waves are synthesized. You guys have any clue? So typically what you would get is a wavetable oscillator. And the reason is that the calculation of a sine wave is fairly expensive, so to speak. In fact, the duration it takes has to do with the precision that you require. So let's just look at a sine wave as it is defined in math, in trigonometry. This is what it is, right? So the point here is that you understand this type of graph. What it means is that we have a function, and a function will produce I should say a direct output, a single output. So the point is that every input, every possible input to the function, every number you put into the function will always yield a single number as the result or the output of the function. So the way we are plotting these graphs is essentially making sure we are inputting all the possible numbers. So that's the x-axis here. And then for each of the input values, if you trace them on the x-axis, you can trace it's a single output value or a single result of this function. Okay, so you see that actually no matter how large the number is that you input into the sine function, it's gonna stay between -1 and +1, the output. Okay, so it's a cyclical function like that. Cool. So the point is that if I have an x value of 0.5 and I want to calculate the sine value of that, actually now I'm there at 1, I can actually trace this graph. To calculate this very precisely, we are actually running a recursive function. So there is no direct computation for a sine function. You have an algorithm that will approximate it. And the more you run the algorithm, the more it will approximate. Okay, and something similar, maybe you guys look a bit interested and puzzled. I believe the Newton's root method is a simpler version of such a thing. Let's see if we find a nice image. The one with the square, the one with the square. It's a simpler converging algorithm like that. I don't see the beautiful graph that I'm normally used to checking out. In any case, I guess it's kind of clear what it means if I say that there is an algorithm and it will approximate. Funny, there's none. And it will approximate the value, and the more you run it, the better you get, the more precise you get. So essentially, you could compute a sine function for every input value or output value, but it is not very efficient. So that's why typically what happens is you get a wavetable filled with sine wave, and then you interpolate and you read from the table, which is much more CPU efficient. Now, there is a third way of synthesizing a sine wave, which is, so there was two ways, right? One was with the math, which is expensive. The other one was with a wavetable, which is kind of math, but then with a trick. And then the third one, you can actually build a model of a harmonic oscillator that produces a sine wave. So if you remember, or you had some physics or something along those lines, harmonic oscillator, for example, is a pendulum. And actually the model of a pendulum is just a few additions and multiplication. It's a fairly efficient thing. In fact, a bandpass filter is something very close to a pendulum. You see, swing in the park, you know, the one that the kids swing on, is a bandpass filter. Does this make sense to you? Because you see, if I'm set on the swing and I move my legs too fast, I won't start swinging. If I move my legs too slow, I also won't start swinging. I have to find the resonance frequency of the swing, and if I push my legs back and forth at that frequency, then I will catch momentum. So it's a kind of a resonant system with a very clear resonant peak. And if there is small amount of energy at the resonant frequency, then this will build up. Okay? The thing to know about the third option in terms of synthesizing a sine wave is that it is not so stable. So if I start to jerk around with the frequency, with the phase parameters, and give it a hard time, it might go to hell. You've seen some algorithms go to hell yesterday, right? Because actually the swing model is also a recursive algorithm. So technically it can also give you chaos, it can also give you resonance, it can also give you stable output. Or I should have said oscillation. Okay, so that's just a kind of an intro so you understand a bit about how sine wave, worth knowing, in analog equipment, a clean sine wave is near impossible. The digital sine waves are always much cleaner than the analog ones. And the reason is that there's always some kind of nonlinearity going on in the circuits, and it can't really produce a clean sine wave. Okay, so actually the textbook thing is that we can produce a sine wave if we take the sine function of a sawtooth wave. Okay, so you see that to get a sine wave, what I need to do in this mathematical approach, I need to put in number 0, I need to put in number 0, 1, 0, 2, 0, 3. I need to go through all these numbers, get the result that will trace out a sine wave, and then when I reach the 2 pi, 6.28, then I can actually start back again at 0. I mean, I could try, I can create an increment that goes on forever, but actually after some time it will run into the limitations of the floating point number or whichever data type you're using. So it's risky to run it forever, just an increment. Instead, what we do is we produce a phasor at that frequency, essentially. Okay, so maybe you remember, I'm not sure how much I've talked about the modulo function, but if I take x modulo 2, that is actually my mathematical phasor or sawtooth wave. So you've probably encountered the term sawtooth wave more frequently as it is used in terms of synthesizing a sound, but actually the phasor is the exact same thing, and typically the name is different. We call it phasor because it is used for specifying the phase of such oscillators. So you see, I'm actually almost there. If I was to take the sine wave, the sine function, actually I can do that as well, that's funny. If I take the sine function of x modulo 2, you see, this is what I get. So I'm kind of running up into the sine wave, but actually I'm not coming through with it. It's just the first bit, less than half of it. So I can obviously play with stuff, and you see if I do a 3, that looks good. Essentially, if I do a 2 pi, I actually get a clean sine wave. Okay? So, you want to do this as a task? Let's see how far you get. It's challenging. I won't let you, go crazy with this. But give it a few minutes. This is your function. Phasor is phasor. Okay? And sine is sine in SuperCollider. So you need to produce a phasor, a sawtooth wave, which goes up to essentially 2 pi. And then you need to take the sine function of it. Okay, so start it. I'll give you 5 minutes or so just to get started. I don't want to talk too much. And then we'll take it from there. So let's look at this thing together. So first of all, a phasor is, it's a triggered one. Okay, so actually for that we need an impulse as well. Well, we'll do it. And then actually, no, I think it's just re-triggerable. Let me just remember this, because I think, let's check the help file. Start and end values trigger input crosses from to its reset position upon reaching the end of the ramp back to its start, right? So it's going to run on its own, but you can restart it. Okay, now that can be useful, but in any case, for us, we can leave the trigger at 0, and then we have the amount of change per sample. It says at a rate of 1, the value of each sample will be 1 greater than the preceding sample. Okay, so actually to control the frequency of this is quite tricky, but let's see. So let's just take a really small number. And then we start the ramp at 0 and we end it at 2 pi. Does that work, 2 pi like that? Yeah. Okay, so I'm totally unsure about this one, so I'm just going to first check it out. And that's what it does. So it takes really large steps, and it does go between 0 and 2 pi, which is a bit funny because I've set the rate to 0.001, and it says amount of change per sample. Greater than the preceding sample. That's really weird. How about this? Yeah, it goes much slower. So it's actually the inverse of that. Okay, so if I take, well, that looks like a very slow one. Let's see. This is extremely slow. I'm a bit puzzled by this, to be honest. There we go. Okay, that's at some, I probably just didn't see because you see I see only a few values. But in any case, now I know that it goes 0 to 2 pi. So what is this waveform? Am I actually hearing a sawtooth wave here? There is a little caveat, that's why I'm asking. If you think it through, I'm not gonna get a clean sawtooth wave. Any ideas why? If I just listen to this the way it is. It has to do with the range, right? So what is the range of a regular sawtooth wave? Just like all the oscillators, -1 to +1, okay? What is the range here? No, 0 to? 0 to 2 pi. So actually what I'm getting out of the sound card is a harshly clipped thing, right? Because it's going to clip at 1 already. I can try to observe that. Scope. You see, that's what it is. It's really heavy clipping going on. And it's a unipolar signal as well, so kind of useless. Now, it seems the scope does not cut it at 1, because actually inside, so to speak, the number is not capped, right? It's still there. It's just that it doesn't come out of the sound card, but it still comes through to the scope, so it might be confusing. Okay, so that's that, and then if I take this to be x, and I output the sine of x, here's my neat little sine wave. Okay? Cool. So now comes the difficult thing. How do I create it such that the period stays the same, but the sine wave becomes shorter? And once it runs through the whole cycle, it starts to mute. Right? So I want to have 0 values after the sine has gone 1 period. And I want a parameter that allows me to pull the sine wave even further in, and thereby get left with more zeros, right? Currently there are no zeros, I just have a clean sine wave, right? It connects at the end. If I mess this up, this is a neat one, if I start to mess it up, I should be able to do this. Any ideas? So you see, you understand that in the cycle of the sine wave, underneath, so to speak, is a phasor running from 0 to 2 pi. You got this one, right? So what I want is to shorten that sine wave. So it means that my phasor has to climb faster, right? So I'm shortening the sine wave. But if my phasor keeps climbing, I'm going to continue drawing the sine wave. Right? Actually, that's probably a good intermediate thing to do. So what happens if I, to 2 pi, add 0.4? So here, I mean, I'm not sure if I can zoom in sufficiently. I don't remember what was the trick to kind of get it to stop. But you kind of see it happen there. That the fact is that it runs over. I have one cycle, and then it runs over, and then starts the next cycle, right? So that's my thing. I would like to have zeros there. How can I do this? So this is a technique which is really useful, and I didn't talk much about the fact that, you see, when we think about constructing things in server, it is a lot like analog modular synthesis, because the tools are very similar. If you were to write a proper programming language code for this, well, you can just say if this, then that. But in the server, we don't have if-thens. So you have to be clever about gating stuff. Okay? And the crucial thing is that if I multiply something by 1, it is coming through unaltered, and if I multiply it by 0, then 0 start coming through. So actually, it is very often the case that if you are clever about creating a signal which is either 1 or a 0, then you can get a sort of an if-then behavior, right? Because that's when it stops and that's when it starts the whole signal. Okay, so in this case, the way we can derive our comparator signal, so comparator is the name that we use in analog modular electronics, I can actually say x is larger than 2 pi. And the comparator will give me either a 0 or a 1. Okay, so in this case, it's going to be 1 when it's larger than 2 pi, it's going to be 0 when it's smaller than 2 pi. And actually, I need it the other way around. So I'm asking, is x lesser than 2 pi? And then what I can do is I can actually take the sine wave of x times c. You see, because when this phasor overruns above, I mean, when it's in the normal range, 0 to 2 pi, then the comparator yields 1. Therefore, x times 1 is just the same signal. As soon as it crosses 2 pi, what will happen is that this will yield a 0, false, and therefore this will yield a 0 as well, which means that I'm going to get the sine wave until it's completed the cycle, and then I'm going to get zeros. So you kind of see it. You see the zeros in there? Cool. So now the idea is to make this grow. Okay, so this was my number that made sure that I overrun. In this case, I overrun by 0.8. But now what I want to do is I want to line from 0, well, to 2 pi. So we get the whole cycle going. Okay, so this will actually start with a complete sine wave, start pulling it in, and it's going to go until it does half a cycle with the sine wave, half a cycle with the mute, with the zeros, and I want this to happen in 10 seconds. Okay. So what's happening now? I still hear a pitch drop. This is a kind of a very tricky way to introduce it, because what happens here, unfortunately, is that the rate of climbing depends on this value. So what I've actually done is I have kept the duration of the sine component, and I've just introduced the zeros after. That's why I have a dropping pitch. So actually the way to do this will be to leave the phasor at that. This is my clean sine wave. And then if I multiply it, x is x times 0.2. Okay, now I'm getting this kind of behavior. So if it is times 1, that should obviously be the clean sine wave. If it is less than 1, let's go 0.9. You see, then it's kind of eating up the sine wave. It's going the other way around. Let's see, 0.8. You see, it's slowly eating it up. And then if I go 1.8, then I get the one with the zeros. Okay? So now I can do this, hopefully. I will take a line that goes from 0.1 and it goes to 20, and it does this in 15 seconds. Okay, maybe just go up to 10, get a bit more transition. Okay, so that's the important thing, that you understand that the pitch that you hear, that we hear, has everything to do with the repetition cycle. The duration of the period determines the frequency and not the content. Okay, so if we look at the spectrum of this, well, there's quite a lot of trash going there, but the point is that if it was ideal without aliasing and all the rest, you would never get any spectral components which are not integer multiples of the fundamental frequency. You see? Because the repetition cycle is such, if you have this repetition cycle, if everything repeats at this rate, the only content that you can have is the fundamental frequency and its harmonics, the integer multiples. You cannot squeeze in a 1.3 factor frequency. Because if I want a frequency which is 1.3 times the fundamental, right, then I would have to have a shorter repetition cycle, right? Which means that at that stage I need to start again and start again, so it's kind of pulling in. It doesn't match the actual cycle that we have, right? And here I have made an attempt to pull in the sine wave, and you see that's what happens. I actually get these things going. Okay? Cool. So that's a bit of math. I mean, the funny thing is that, if you get, your understanding down to this depth of stuff, it will just simplify your life. Hopefully. I hope you'll have such a life that will be simplified by this understanding. Okay? Cool. So let's see. Let me give you an exercise whereby I ask you to loop a noise sample. Okay, so I'm gonna do this as a kind of, okay, let's just start from the UGens. Okay, so essentially we have plenty of buffer UGens. Okay, and these are essentially, you have buffer UGens, which are obviously audio rate beasts and run sound, but you also have offline buffer creation tools, classes. So in this case, in order to read a buffer, to play it, I think the simplest thing will be buffrd. Okay, so let's check that one out. Buffrd, I'll actually play buff. The nice thing about buffrd is that it works with the phase. Okay, audio rate modulatable index into the phase, and it says only offers precision for addressing this duration of time. So you see, the wave we've handled, the sine wave just now, was with a phaser. We've actually went through the sine values with a phaser, with an increment. And buff read does a very similar thing, only it doesn't read a sine wave like we did now, but it reads whatever is in the buffer. Okay, so that will be one tool. Let me spell out the task. So play looped noise with different loop duration. So we see what's happening. This is our task, and I'm going to make it a bit challenging because I'm going to only tell you to use buff read with a phaser for reading. Okay, and then in terms of creating the buffer, here is the class that talks to a buffer. I mean, there is things to do also with initiating a buffer, allocating. Okay, so you see this here. Well, I'll just copy it there for you. Okay, so you will be able to allocate a buffer, and then there are different ways of populating a buffer. So we can read from a sound file. There's many things we can do. Read channel, it's similar. Read not update. Queue sound file. Load collection. Okay, so this allows us to create a set of values with any way we want and actually fill the array. And here is the exact sample that we need. Okay, so here we have filling of an array, float array, with random values. Okay, rand.to is a bipolar noise. You see between -1 and +1. So that's doing that, and then you have to load collection. Now this you can execute before running it, because once it's there, then it stays there. Okay, you can plot a buffer like that. Okay, and then this is now done, and now the task is to actually create a playback here. Play which will work with buff_rd. Okay, so that's the task. Let's see if you can, because you see, I mean, one thing is to be able to use the tools that I show you and kind of rethink or make it more complex. But now the task is to actually discover how to use a tool. Okay, so I'll give you 10 minutes for this one, and then also a 10 minutes break, so you can work it anyhow you like. So let's call it 20 past, so we're gonna start at 40 past, okay, in 22 minutes. So I'm gonna leave that on the screen for you. Okay, so let's check it. So first of all, let's check this buffer read. So in essence, what you have is the option to read the whole buffer in its original duration. So I've seen you guys use this one, yeah? So now what it does, it actually takes an LFSO, which is another phaser, slightly easier to control because you actually have the frequency parameter, and the frequency parameter becomes the actual reciprocal of the buffer duration, right? So in this case, my buffer duration is 1 second, the one that I've defined here, 44,000 samples. So, oh, it's actually 5 seconds, sorry. So it's 44 times 5. So actually, what will be the frequency here? Well, it's supposed to be 1/5. Okay, and then the other thing that it says is that the range of the phaser will be between 0 to the buff frames, which is essentially the number of samples in the buffer. So this code, what it does, it runs the original buffer at the original duration at the original sample rate. Okay, so actually what I can do here already is the only thing I need to do really, because this kind of buff frames, if you see, if I have this phaser now, which is really long, it takes 5 seconds and runs through all the samples. That's what I have now. Now, if I increase the frequency, but keep the range, right, then I will have a steeper read, which essentially means that I'm skipping sample values, right? If I make this 1/5 duration, but still the same maximum value, it will go 5 times up in the same amount of time. So actually it will read every 5th sample. It won't read all the samples. Make sense? So the task was to play loop noise with different loop durations. I mean, the point is that noise, white noise, as you see it here, is just a bunch of random values. So it doesn't really matter if I skip samples. That is the point. Okay. So actually what I can do here already, if I put in number 1, then technically I am repeating 1 second of noise. If I put 5, then you hear it already. You see? So that's the interesting thing, that you see this buffer is filled with random values. All of these are totally random values. And the fact that in this case I actually have only 9,000 random values, a bit more, right? 1/5, makes it so that we actually detect the repetition. You see, this is supposed to be kind of really. You see, because we do detect the repetition. And it's only 1/5 of a second. And there is no recognition really, because it's all random values, right? If I fill this buffer with a different set of values, so now all the numbers in the buffer are different, but they're just as well random values, I still hear the actual repetition cycle in the noise. And then further, if I actually take 95, still don't detect the pitch. 195, 795. Ooh. Looks like I'm actually now getting in trouble with these buff frames. So I'm probably want to, yeah, I would need to calculate to make sure that I'm reading sample by sample. That would be one of the options, because here actually I'm getting some kind of weirdness happening as well. Okay, so just a little excursion into buffers and stuff like this, just so you see how it's how it happens. Cool. I'm not sure, what are you guys feeling like? What was the? I mean, this is the last class. I mean, probably December. We still didn't fix the dates, but I'm hoping for the same class times. We can do a bit more, but for now, this is supposed to kind of wrap things up. We didn't really go into any more advanced things. One of the big chapters in sound synthesis is physical modeling. And it's theoretically heavy and coding heavy as well. And it's typically yields fairly sterile sounds, I might say. Unless you really work it. But then the other thing that I think is worthwhile doing now would be granular synthesis, a bit of that. You've probably heard about this term before. There is a large theoretical chapter that we could cover. I'll maybe pluck out a few interesting things. So I guess you all understand that it's about small, short grains that are repeating, or that are occurring, I should say, very frequently. The thing about granular synthesis to understand is that because of the amount of parameters, so typically one grain may have 5, 10, even 15 parameters. And then if you have 1,000 grains per second, the number of parameters is huge. So you don't really get to control them other than statistically. Okay, so typically with granular synthesis, instead of having a parameter that actually fixes a value, we have parameters that describe statistical processes. So didn't go too much into this, but it's a worthwhile term to know, which is equal distribution or flat distribution. So typically when we take a random number generator, it is flat distribution, which means that all the outcomes have equal likelihood. The nice thing is that we can create many different random number generators that have different distributions. You have things like binomial distribution, which has more extreme values. You have the normal distribution, the Gaussian, where most of the values are in the middle. You have exponential distribution, where you have more values to the side. And the good news is actually that you can even draw. There is an algorithm that allows you to draw your own distribution. So you can actually do this fairly simply. In Max MSP, you just need a night table, and it gives you a custom distribution. So in essence, that's what we're looking at. So let's start a new chapter here, and let's check out grain sin to start with. So this is UGen that produces sine type grains, and it has a fair few parameters, starting with number of channels. Okay, let's do something stereo. Then it needs the trigger. Okay, so the trigger needs to be, as you hopefully remember, any signal can be a trigger. If it crosses 0 to 1, then it will act as a trigger. So we actually have two options here, generally speaking. One is to have a regular trigger, and that would yield what we call synchronous granular synthesis. Or we could have an irregular trigger, which would give us asynchronous. Okay, so to start with, I'm just gonna do an impulse. So we have a regular trigger at 99 Hertz. Okay, then we have the duration. And the point here is that this can be a fixed value, obviously. But it can also be any signal generator, in which case it will be sampled every time when the trigger happens. Okay, so, well, what I'll do here is I'll do an LF noise as 0. I don't need interpolation because it's being sampled and held. Well, let's do AR. This is also not very significant. What is significant here is the range. Okay, so range I will take from very short to fairly short. And you see the way that the number of... oh, that's interesting. Something new for me. I'm just trying to make sure that we can read all these in a kind of transparent way. So here we had, I've lost that. So we had number channels, 2, trigger, impulse, duration is a random value. And actually that kind of randomness is probably welcome for other parameters as well. So for frequency, we will have values between 300 and 500 Hertz. And then pan, we can do that as well. Let them be panned randomly, in which case -1 to +1 is fine. Next one is env buff num. We don't need to work with that. Max grains, that's all fine. Okay, so hopefully this gives us a little grain sin. Nope. Impulse AR, let's see. LF noise. Number channels, trigger. Okay, frequency. Can anyone spot anything funny here? Let's see, how does the help file do it? I was trying to get this impulse KR. KR, would that help? Grain sin. KR. Let's just try this one then. Oh, it looks like something else has happened here. Give me a sec, give me a sec. Where's my... there we go. Okay, back to reality. Hopefully, does this work? There we go. Okay, so I have a range of frequencies, range of durations, and range of panning values. Okay, what do you think? Why do I get these weird artifacts? I don't get these clean sine waves. You've heard it. It's a bit funny. It doesn't really. Well, first thing you might think is it might be distorting, right? Because they're not clean sine waves. Well, I can check that by making it softer. Okay, so indeed, it is a bit cleaner. So why would it distort? Well, it has to do with the overlaps, right? So here at this stage, I'm having durations between 100th and 1/10 of a second, right? And I'm having about 100 of them per second. So there will be overlaps. Now, I'm not sure if it's really interesting to observe. You see, the fact is that my trigger here, the impulse, is a steady trigger. But actually I get this variety going, I get this fluffiness going. Why is that? Well, most likely it has to do with the fact that I have random duration. So now I have no random duration, and also I have random panning. Let me make that 0 to 0 as well. Okay, and I still have random frequencies. Okay, oops. So those are the parameters. Okay, so I will give you a little task now. What I would like you to do is synthesize a sound whereby things go from center to wide and back to center again. Okay, so this time it's a kind of a, well, I hate to call it musical, but perceptual at least, definition. Okay, so see if you can do that, right? So get it to grow wide and then to grow narrow back again. Okay, so with this one, the point is that the panning parameter here is currently a noise signal. Okay, so it means that it's already giving you randomization. So with this case here, well, these are a bit too long. Let me just make sure I have something which will be more audible in the end. Much larger range here as well. Hate those sounds. Okay, so this is supposedly center because now this noise generator has a range 0 to 0. Now if I try 1 to 1, that should give me one channel only, and -1 to -1, that should give me the other channel. And then obviously -1 to +1 gives me the breadth going. Okay, so actually you see these two values are the ones that control. And it's back again the same story, right? How do we control ranges? Because this is a bipolar range, it's enough to multiply it with a value that goes from 0 to 1 to make it broad, and back again to 0 to make it narrow. So there's multiple ways of doing this. I'll just use, I was thinking of using a line, and let me just remind myself, but I believe that it has no issues with lists, or it actually might do. I probably need an envelope like that if I really want to list. Yep. So let's use an oscillator then. So we've already seen how this is done with the sine oscillator. If I take it at a low frequency and with the range 0 to 1, then I should be getting that thing. Let me just check the brackets. That range times sine, that's that times 0 to, okay. You guys hear it? Yeah? Going back and forth? Okay, so task B, let's do a few exercises with this. So now I would like to make the frequency range go up with the width. Okay, now I will ask you to using a single modulator. Okay, so here I'm modulating the panning with the sine wave. And now I want the frequency range also to move up and down, but using the same sine wave. Okay, let's see if you guys can get that going. Let's look at it together. So first of all, very useful to remember is that if you want to use one thing multiple times, you just store it in the variable. Okay, because if you do this twice, if you have this sine oscillator code twice, you're running two different modulators, right? So what I'm going to do then is cut this and multiply by m, and then define m to be this modulator. So I can just test this. It's sometimes useful to keep testing, and that seems like it's doing the thing. Now, the other trick to know is that what I can do is I can use dot range multiple times for the same oscillator. So actually here, when I modulate the panning, the range is well between 0 and 1. And here, when I modulate the frequency, if I multiply this, with this, well, part of it will be inaudible because the frequencies will go down to 0. In fact, what happens here is that if you imagine that this is number 0.5, then this will be 150 and this will be 300. So it seems like the frequency range is shrinking. Is it? Or is it not shrinking? Well, actually, as far as the exponential axis goes, it's not shrinking, right? Because the multiplier stays the same, right? So between 300 and 600, we get an octave. Between 150 and 300, it's also an octave. Now, between 0 and 0, it's not an octave anymore. Okay, so something does happen in terms of it shrinking once we approach the 0, or indeed once one of the values snaps to 0. And then very shortly after the other one snaps as well. But in any case, what I could do here is I can say, well, how about I run it from 1 to 7. Can you hear the stereo thing happening as well? Cool, and obviously what I can do then as well is I can inverse it. I can actually run it such that the lower go broad and the higher pitch goes narrow. I imagine that's audible. Okay, so the last exercise for today then will be to make the triggering random. Okay, such that as randomness increases, the duration becomes shorter. Okay, and be efficient. Reduce the amount of generators used. Okay, so this is my triggering parameter. So now it's a cyclic one and it needs to be a random one. And this is my duration parameter. Well, currently it's at fixed value. So try to get the C task done. Okay, any luck with that? Slightly trickier. Mm-hmm. So the thing to realize here is that, first of all, the triggering parameter, right, what it does is when this signal goes from negative to positive, it will trigger a grain. So the point is that if I put an LF noise up there, what's going to happen? Well, first of all, you have to realize that the LF noise 0 is your stepwise random, right? It's non-interpolated. So what will happen is that 100 times per second, regularly 100 times per second, it will jump between two values. However, you don't know whether this jump will be non-positive to positive. So you are not sure that every jump will trigger, but the jumps are actually regular. Okay, so you kind of get a randomness there, but it's not controllable. Right, because you just don't know when it's gonna cross the 0 line, so to speak. So the thing to do, there's multiple things you can do, but actually the good thing to know is that we have a dust.ar, which is your random timing triggers. Okay, and it's actually one of the nicest things as well. I can have it at 20 just to test it. Okay, so that is now my density. Let's see if I can get it much denser as well, I imagine. Okay, so that's now my density, and then the task was that as the randomness increases, the duration becomes shorter and reduce the generators, which means I'm going to still use the M. Okay, so here I will multiply this with M and M, what should I do to it? Well, let's just give it a range. That's the simplest thing. So I'm going to go with the range of 1 to, well, actually, if it's 2000, let's start from 20. That's better. And then I will go from 1 till 50. And then I want, so as this increases, I want reduce the duration. Okay, so this means, I mean, duration is currently a fixed value, so I might as well keep it a fixed value. It was this, and now I want it to go opposite, so I will multiply it with m.range with the opposite sign. So I can probably go 20 times to 0.1 times. Oops. Semicolon. No, that's semicolon. Yeah. And that's the nice thing about short durations, that you get this really crackly type thing rather than these sine waves. And now, because everything is running off a single oscillator, obviously I can take it much longer. You see how that range, when you start to lose pitch and get these crackles, is quite interesting like that. Okay, guys. Well, that's that. Thanks for your attention and hard work. And worth saying, so for this subject, the exam is some music. Okay? You have until January or so. We will meet. In fact, you guys want to meet online as well in the next few weeks? Once or twice? Okay, I'll send you probably just an hour or so. I won't be introducing new things, but what I would like to ask you to do is start working on some music with this. And then when we have these meetings, if you bring something in, show me the code. You know, if you can formulate what would you like that is difficult, or, you know, just some general talk about this, that'd be great. Okay, so no strings attached. It has to be mainly SuperCollider. If you're producing a track which is in a different genre, or, you know, has some very specific things, you can always add stuff to it. But I would like that the SuperCollider sound is the backbone of the piece that you're making. And you will need to submit the sound and the code. Okay? Please, if you work from example codes, which is fine, please specify where it's from. And actually the best practice is to keep a log. Okay, so you say, okay, I've done this, but actually the source file was this. I'm not sure how the language models deliver in SuperCollider. DeepSeek did some good things, not quite perfect. But also if you use that, it's fine, but just please make sure you reference it. So you say, okay, I've asked for a sound that sounds like chicken in SuperCollider from DeepSeek, and this is the code that I had, and then I changed, and then, you know, then you do something to it. So just so I see the progress. And, you know, I can mostly advise you to experiment, you know, see how far you can get. And, you know, if you can actually tell us about what you tried, how it worked, and kind of give us a sense of a process that you've been through, I think that's very valuable. Okay? Cool. Well, cheers.